This is another non-homogeneous higher order equation, but this time the g of x, or the expression or the function that can be found on the right hand side of the equation, is exponential in nature. It's not equal to 0, because if this is equal to 0, then we can simply use the same processes of solving homogeneous higher order equations. This time, we have an e to the power of 2x, which is exponential in nature. Hence, we'll be using a different form of general solution. The general solution is expressed in this manner. Y is equal to y sub c plus y sub p. Y sub c actually is similar to the process of solving homogeneous higher order equations. That is, again, if our g of x is equal to 0. So it's still part of the process here, and we are determining the roots of the auxiliary equation equivalent to this equation, and there are 4 different situations, like whether the roots are real and distinct, or they're repetitions, or imaginary as such. We're going to follow the correct general solution for y sub c. Now for y sub p, this is what we call as the particular solution of this equation following the solution of the coefficients following these forms. Since our g of x is exponential, please proceed to the row number 7, considering exponential forms of g of x. The form of y sub p we are going to use later is a e to the power of the exponent of e. Since our e here is expressed through the exponent of 2x, so we also have here 2x in this case. We are going to solve for a later on, or coefficient a, so that we will have an exact solution for y sub p, which will be combined to y sub c. So let's start with y sub c. As mentioned, it's a complementary solution if our given equation here is homogeneous. Hence, we will have here, we can write our equation in a form of an equation with differential operator d. Hence, you will have here d squared minus 2d plus 1 multiplied by y equal to 0. Hence, its auxiliary equation in terms of m is expressed as m squared minus 2m plus 1 equal to 0. The task here is to solve for the roots of this auxiliary equation and determine later on the correct general solution depending on the nature of the roots. This is factorable. We can have here m minus 1 and m minus 1 equal to 0, because as you will multiply them, you will get m squared minus 2m plus 1. Hence, our first root is equal to positive 1, and this is also the same root for our second. Hence, that's 1. Hence, we have roots that are distinct. Roots that are real, but we have repetition, specifically multiplicity of 2. In short, the general solution for y sub c will follow the general solution form when our homogeneous equations has auxiliary roots, or roots of the auxiliary equation being repeated and real. And it's expressed in this manner. E to the power of your mx, your m is your root, times c sub 1 plus c sub 2x. We just stop here because we have multiplicity of 2. If we have multiplicity of 3, then we add one more term. So with that, our y sub c is e to the power of your first and your second root 1x. C sub 1 and c sub 2 will retain as they are, and times x. In short, it could be y sub c e to the power of x c sub 1 plus c sub 2 x. This is already acceptable as the complementary solution of our non-homogeneous equation here. With that, let's proceed to our y sub p. Again, the goal now is to come up with the value of our a coefficient, so it will be exact, and it will be added to our y sub c for the general solution. Take a look at our given equation, because we will be substituting y sub p to all of our y. In short, for our first order derivative of y and second order derivative of y, we also need to take the first order and the second order derivative of our y sub p. And since our y sub p is in the form of e to the power of 2x, its first order derivative is still ea times e to the power of 2x using the chain rule, then the derivative of our exponent, which is just 2. Hence, the first order derivative is 2a e to the power of 2x. Then, our second order derivative will have, again, treating this as constant, you will have, let's put them here. Second order derivative of p, we have 2a times the first order, the derivative of e to the power of 2x is still e to the power of 2x times another derivative of the exponent, which is 2. Hence, the second order derivative is 4a e to the power of 2x. Now we have this and that, and earlier a y sub b. We can now substitute them as we would like to solve for a on our original equation here. And the original equation is expressed in this manner, is equal to e to the power of 2x. So we simply use the derivatives of p, y sub p and y sub p here. So you will have 4a e to the power of 2x minus 2 times this one here, 2a e to the power of 2x plus your y sub p. Of course, we still have one more step here. It will be like this as we substitute y sub p to all the y's here. That's why we have this. Okay, so plus your y sub p, which is a e to the power of 2x. These are all equal to e to the power of 2x. Okay, so combining them, 4a e to the power of 2x minus 4a e to the power of 2x plus a e to the power of 2x is equal to e to the power of 2x. This will become 0. A e to the power of 2x is equal to e to the power of 2x. And when would this be true? This would only be true if a is equal to 1. Or as you divide both sides by a to the power of 2x to solve for a, that's just equal to 1. This is the value of our a. Hence, going back to our y sub b, which is supposedly a e to the power of 2x, and since our a is just 1, so you will have 1 times e to the power of 2x. Our y sub b is just e to the power of 2x. We now have y sub b. Earlier, we already have our y sub c. Since the general solution is just the combination of both, so we'll have our final solution here. Y is equal to y sub c plus y sub b. Our y sub c is this one here, e to the power of x times c sub 1 plus c sub 2x plus your y sub p e to the power of 2x. This is now the general solution of the given non-homogeneous higher order equation. So please take a look at all the processes involved here. Of course, again, we use this because we already have a table representing the form of y sub p if our g of x is exponential in nature. Thank you very much for watching.